I can use in the cartoon to describe the Fourier series. I have all kind of random wave. Right? This is maybe it's your perturbation. Okay, maybe it's in reality you have this kind of arbitrary wave. However, all these arbitrary waves can be decomposed. A1 times what? Sine cosine function plus A2 times 是相乘的意思。Right? Plus. Right? That's a Fourier series expansion. Right? Mathematically just like this. Any wavelength can be superimposed by sine cosine function, multiplied a specific amplitude and multiplied together. That's a Fourier sine or Fourier cosine function. Series expansion. So this becomes so-called a mode, right? This is a basic mode. Right? Sine cosine function is a basic mode. Okay? Basic mode. So we call it the normal mode. Okay? Because we only use in the very basic mode to test. Okay, that would be. If you want to use the more complicated, you can superimpose together. Okay, without any difficulty. Okay. Introduction until here. So let's try. Okay. What do I mean? Okay, AB concept here. Okay, how do I apply into this flow system? Here is a physical problem we have. We have two flow. Okay, we have interface here. Upper flow with we have a density ρ2, velocity u2, and then bottom below the interface here we have a velocity u1. Our density is ρ2. They are immiscible. For example, 它们不互溶的两种液体。Okay, they may be different fluid. Okay, and they are immiscible. And so once I have this velocity and density different upper and above and under, okay, this interface, and I would like to understand this flow system is a stable or unstable. So this is a flow system, okay, for this physical problem, for example. Okay, so how do I test? How do I test this flow system? It's a stable or unstable. Again, on the interface here, I try to generate what? A small perturbation, and to see eventually this perturbation to go with time or decay. Right? And we can check this flow system is stable or unstable. Right? That's how we check. Okay, the concept looks like this. Okay, then to check the stable unstable, I just mentioned you have to check the sigma I, right? Imaginary part of sigma. If this is greater than 0, our flow is unstable. If sigma I is less than 0, our flow is stable. Okay, so let's do it. Okay, let's do it. First, okay, this is the velocity. Okay, ui, I need, okay, I equal to 1 is below the interface. This is O1. Okay, I equal to 1, and I equal to 2 is above the interface. Okay, so all the flow, this velocity can be written as what? Ui ex times plus a gradient vi. And what's this? What's this? Okay, why do I want to evaluate my flow field above or when I equal to 1 and below and I equal to 2? That's reverse. When I equal to 1 is below, right, and I equal to above, right? And why do I want to introduce the flow field here? Can be written as like this. What's the concept between that? Since we have a fixed velocity u1 and u2 here, right? This is the constant, okay? And this u1 and u2 is a constant. This is flowing at a speed. However, near the interface here, because I have a small perturbation, right? I input a small perturbation here. The flow field near the interface will be perturbed. Right? Only the near the interface here will be perturbed. Far field, what? Will not be perturbed. 只有在流场在这个界限附近的流场才会有一些些微的改变。远离这个界限，远离这个界面的，它还是回到 uniform flow。 Everybody agree with that? Okay, so that's the concept. So the velocity above and below, I can read it like this because this is uniform flow, right? This is a constant. So I can superimpose this constant with a velocity potential. This velocity potential is due to what? It's due to the perturbation. Right? Due to I introduce a small perturbation. And then this small perturbation can cause our flow have the variation here. And the total flow will be superimposed my uniform flow plus this perturbation velocity. Right? That makes sense to you. Okay? So I can assume the velocity field can be written like this. This is a perturbation. Okay, this is a perturbation. Velocity potential for the perturbation, due to the perturbation. Okay, if you agree with that, I can written like this because this is our physical problem. Okay, and the velocity can be kind of using this. Okay, so instead of solving the velocity potential represent all the flow field, I only solve for the perturbation velocity potential, right? Phi here. Phi is due to the perturbation. Velocity disturbance due to the perturbation. Okay, here is our substantial derivative, if you remember. Right? This is substantial derivative. So about this physical problem, what kind of boundary condition we should satisfy? What kind of boundary condition should we satisfy? We have first boundary conditions in this chapter, the beginning of this chapter. What's this? So-called kinematic boundary condition. Remember, for the kinematic boundary condition, all the fluid particles on the interface stay on the interface, right? And how do you write down the equation for that? All the fluid particles, follow the physical sense you have. All the fluid particles on the interface is this, right? Y equal to eta, that means y minus eta equal to 0. And all the fluid particles on the interface, follow fluid particles to ddt. On the interface, this fluid particle. That's physical, meaningful. I just expect. All the fluid particles stay on the interface. If you follow a trend to see when the time change, it stay the same, stay on the interface. That's the equation. Okay, that's the boundary condition. So we call this the kinematic boundary condition. Okay, so that's at the beginning, okay, of our course. We apply that. Okay, so we apply this. Remember this kinematic boundary condition. Okay. So ddt is this, right? This is substantial derivative, should be like this. So if you do that, partial, ui is this. So I did because in your lecture note may not be clear. I did a little bit here, maybe here, not here. I didn't did it, sorry. Anyway, you substitute this into here, okay? And what happened? You can get this. You can get this. Can you do that or not? Okay, let me do it again. Ui dx, this is the vector, right? Cross gradient v, that's our ui, right? This ui dot what? This is ui dot gradient, right? Dot del. Dot del, right? And del is v del. And since we are del is what? It's a y minus eta. So this is del, y minus eta. Right? That's it. Once you apply this, okay, and then here's the y minus eta. So partial y minus eta, partial t. And since the y is independent with t, so only eta is function of t. So the r becomes partial eta, partial t, minus sign e. And then the second term here is this term here. Ui dot gradient is this one. Okay? And then as you can see here, this is ui, right? This is acceleration plus Phi, okay, and dot. Okay. For this term here, this is acceleration. So acceleration only dot with what? With acceleration writing in 2 dimensions. This is the tail of this become like this. So for this term here, okay, y is now functional x. So this should be simplified as partial a dot partial x minus sign, right? This should simplify as like this. And y is a dot is not functional y. A dot is only function xt. And so partial y is equal to y. Partial a dot partial y is equal. So this is equal to y. Okay. So here's the ex direction. So dot with ex. When ex dot dy whatever equal to 0. Okay, so this you have only dy with partial a dot partial x minus sign here. And this term marked by this term. And what's this? This term, okay. This term is again you can separate the partial x, partial y, partial y, dy, right? Okay. So as you can see here, okay, ex times this. This is a very small number. This is already perturbation. This is also perturbation. Two small numbers multiplied together is even smaller. So we can negate the second order term. So we negate the second order term. Okay, this is second order term. Okay, we negate it. Okay, the only term left is this term multiplied this term. Because this is all ey, so it becomes plus. Okay, partial b, partial y. Okay. Right. So end up with like this: partial b, partial y, and this is term, the head. And the first term here is only the partial a and partial b. Okay, I don't think I would like to do it, but you got a point. Okay, you have to evaluate like this. Okay, so from here, okay, by substitute y minus a dot into this equation, you got this. And this is because this is second order term, we neglect the second order term. Okay, this is very small number, and this is even smaller. Okay, multiply a small number, even smaller is good. So our boundary condition, kinetic boundary condition for this physical problem, okay, when I introduce this, okay, it will become like this, right? So partial phi partial y is equal to what? Partial phi partial y, okay, at the interface is y equal to 0. Remember, what's the interface here? My coordinate system here is y equal to 0 at the interface, right? This is y. Y equal to 0 is the interface, okay? So partial phi partial y and y equal to 0 is equal to what? Equal to this term. This is all minus sign, minus sign. Move to the right hand side equation, become partial a dot partial t plus uy partial a dot partial x. So that's a new kinetic boundary condition for our physical problem for this case, right? This is physical problem for this case. Okay. Next, what do I have for the next boundary condition for this physical problem? We introduce dynamic boundary condition, right? Another dynamic boundary condition. Dynamic boundary condition is satisfied on the interface. That means the pressure here should be equal or not equal due to the subtension effect. But here we didn't consider subtension. Okay, we just neglect subtension for this physical problem. Okay, if you consider subtension, the pressure up and down here may not differ. Okay, but right now we assume there's no subtension. Okay, right. So dynamic boundary condition is this. Okay, this is our actually this is our Bernoulli equation. Okay, this is Bernoulli equation. The Bernoulli equation relates to the velocity field to the okay. So this is a Bernoulli equation, and we have a constant pressure surface. So this is constant is equal to a pressure, and since we have a constant surface pressure, okay, at the interface, so this should be satisfied. Okay, so this is called a dynamic boundary condition. And dynamic boundary by apply our phi, this is a velocity. Okay, look like, and then this ui and ui should be using this, right, into this solution here, into this boundary condition here. And I did a little bit here. This is ui, this is our Bernoulli equation, and ui and ui already using the just I described here and here, right? This is our uniform flow, okay, and with the perturbation velocity potential, okay, or perturbation velocity. As you can see, you multiply this ui times ui give you the ui squared, because ex dot ex give you 1. Okay, and then we have the ex dot with this gradient phi I, and the gradient phi I only when ex this has to be ex2, so it become partial phi partial x, right? So this is a ex dot this partial phi gradient phi I, and gradient phi I only value, okay, for this ex dot this, if this is ey, that will be the equal to 0. So only term you should have is ex here, and ex here is give you the partial phi I partial x here. Okay, and then because you have this multiplied by this plus this multiplied by this, so you have 2 here. Okay, and then the ex dot ex equal to 1, so you have this here. So eventually, okay, we have this equation here, and as you can see, ui is a constant. So this is once you assume the constant, this constant can be moved to the right-hand side equation. So constant minus this constant give you a new constant. So our new dynamic boundary condition reduced to this. Okay, so this is a dynamic boundary condition. We just copy here. Okay, so y equal to 0, we should satisfy this dynamic boundary condition. Okay. Okay, finally got the equation, but I run out of time. Okay, maybe on Thursday. Okay, not a Thursday. Today is a Thursday already. Next Tuesday, right before before the New Year, possibly we can finish. Okay. Yeah, so we're almost finished.